All right, another one. We got another paper here from 2024, so it's mechanics one from Edexcel. Let's get started. So first question, what have we got? Some particle up here. It has half a kilogram of mass. It's at rest on a rough horizontal plane. Find the magnitude of the normal reaction at P. Well, of the plane on P. So what's it going to have? Some weight coming down. So m times g, half a kilogram times by gravity. Some reaction force going up. We'll just call that R for now. Let's then balance those forces. So taking the up components, what do we have? We have R. Taking the down components, we have that half a g, and they're going to be in equilibrium. So this will equal 0. Rearranging this for the R, what do we have? The R is going to be g on 2, or half a g, either way you want to face it. Looking at the second part then, we now have the coefficient of friction is 2/7. I'm going to move this question out of the way, just to not have that over the top of us. Put you up there for a sec. So yeah, 2/7 for mu, and carrying on for the next bit, we're told that we have a horizontal force of x newtons. So let's just apply that to the right. If we did it to the left, it wouldn't make a difference. It's just a mirror image. So our friction should be acting to the left-hand side. We could write just F or FR for friction, but we know, because we are in limited equilibrium, that our friction is equal to mu times R. So therefore this should be mu, our 2/7, times the R. So the 2g that we found above, sorry, g over 2. So what's that going to give us? That's going to be a 1/7 of g. So g on 7. And then the same idea. Let's resolve forces horizontally. Pulling us to the right is x. Pulling us to the left is g on 7. We're in equilibrium, so they equal 0. And therefore x must be g on 7. Lovely jubbly. That all looks good to me. Everything nice and simple in terms of g. That's what we like to see on these sort of questions. So let's keep going. Question number 2. We have a speed time graph. So we have a speed time graph for the motion of an athlete running a 200-meter race in 24 seconds. They start from rest, accelerate at a constant rate, reach a speed of 10 meters per second at 4 seconds. Constant speed after that of 10 meters per second until they get to 18, and then they can decelerate again at a constant rate. So that constant rate just tells us all of these are straight lines. Yeah, there's no kind of curved here. So using the model, find the acceleration during the first 4 seconds. So if this is speed, this is time. The acceleration is given by the gradient. So it's going to be 10 take away 0, divided by 4 take away 0. So 10 over 4 should be 5 over 2 for that one. Next part, find the distance covered during the first 18 seconds. So again, this is a speed time graph. So our distance is given by the area. If we look at kind of the first triangle here, we've got 10 and 4, times them together get 40. Half that, we've got a 20. This big section, it's going to be 14 long. So 18 minus the 4 to give us 14. 10 high, so that's 140. 140 and a 20 gives us a 160 altogether. And now when they've bonked at the end, they run out of energy. We need to figure out kind of how much do they slow down to. So they did 160 at the start in terms of distance. They must have that 40 meters at the end to go. So this trapezium must have an area of 40. So let's think about that. The area for trapezium is half of A plus B. A and B are the heights in this case. So 10 plus U times by the width of the trapezium in this case. Normally they call it height, H for height, and you have the trapezium fallen over, but here it'll be this sort of width of the trapezium. So times by 6, and that equals 40. Rearranging some bits, this is going to be a half times 6 is 3, so 40 over 3, take away 10. 10 is 30 over 3, 40 over 3, take that over 3 is 10 over 3. So U should be what, 10 over 3 or 3 and a third, which yeah, a bit slower. So it's third of the speed of the word going up. That all looks good, and it's nice and simple, nice straightforward. Like always, I'll go with everything, and I will check at the end to make sure everything's fine. But that all looks good to me. If something pops up straight away that looks horrendous, we will have a quick investigation on it. That looks good. Let's go to number 3, where it is. If you never need all this space. If you do something's gone wrong, you shouldn't need all that space. So what have we got here? So first thing I've spotted is just like we have some angle. So if tan alpha is 5 over 12, we know that sine alpha is going to be the 5 over 13. And cos alpha is going to be 12 over 13. This comes from a triangle. If we had like a right angle triangle, alpha down here, 5 opposite, 12 adjacent, gives you 13 on the hypotenuse. So I'd always do that first and always put it up here, just so it's, you know where it is. Don't have to go searching for it. It's just straight away in the same corner every single time. After that then, let's put some forces on here. We have a particle of mass m held at rest. So it's going to have some mg coming down this way. It's held at rest on that surface, so there will be a contact force or reactive force. On a rough inclined plane, so friction coming up here. And we don't know the value of friction, but we do know underneath here that our mu is less than 5/12. So on this force, I'm going to put mu times r. You can just put friction, and most of the time it will just become ur. The one case is like if we're not in equilibrium. No, if we're in equilibrium, but we're like not at the point of slipping, then this is not true. It should be f, and it will just be less than this value basically. But 95% of the time, it is going to be this, as long as we are on the point of slipping. You can look at the next part. It's released from rest and slides down the plane. So if we're ever moving, this is fine. So that's all good. We got an air resistance. We want to find, in terms of g, the normal reaction force. For these mechanical, like resolving forces questions, often you can just get the equations and then later on see what they wanted. So like if you look down here, it's acceleration. Generally, if you find acceleration, you've solved everything else. And that's true here. You would have done A and B just to get acceleration. So let's do that. Let's resolve the forces. We have choices here, like horizontal, vertical, in line with the slope and perpendicular. When we look at it, these two forces exist on the slope and perpendicular axis, and just the weight exists on the horizontal and vertical. What that means is, if we were to take components horizontal and vertically, these would exist in both, and this would only be one of them. And vice versa is true if we go this direction. These exist in one, and this is in two. So to get the fewest number of terms, we want to go on this one where our axes match the most number of forces. So that means like this one doesn't exist in this axis, so it gets eliminated. Not only does that simplify our equations by fewer terms, but it also means we're able to eliminate entire variables. Mu only exists in this axis. So if we resolve our forces perpendicular to that, mu does not have a component there and therefore does not exist. So our equation will solve simply for r, because there's no other unknowns that are like kind of not on here. If we cross out these forces, what's left over? R and mg. So we'll solve immediately for r. Then we can resolve this way and solve immediately for mu. So let's do that. Going against the slope, we're going to have pulling us up is going to be r. Pulling us back down then is going to be the component of the weight going this direction. So if we have alpha in there, this is whatever adds up with that to make 90. And this side therefore is alpha. Again, if you have a difficulty moving the angles around, go and draw this little thing where you have horizontal, vertical, the slope, and the perpendicular. And we can see alpha is in this angle. So it's between the horizontal and the slope. So we can put that in there, like it's that little one, isn't it? And it's going to just alternate around here. And then you can just match them up, like I have vertical and this one, vertical and this one. Yeah, my angle should be in there. We'll use that later on for some other bits, like in moments and stuff. It works out quite nicely. So if you're ever stuck, unsure how to get the angles around the place, do this little kind of pinwheel double axle thing. So using that, we want to have the component of the weight going in this direction. So we have this way, angle in between. So our angle is nice and cozy in there. So we need cos. So mg cos of alpha. And we actually know cos of alpha is 12 over 13. So I'm going to put that in there straight away. So this should be 12 mg over 13. And this is all going to equal our net force, but we are sliding down the plane. Are we in equilibrium? It's held at rest. Blah, 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 blah. Slides down the plane. Doesn't say equilibrium, but I'm going to assume we're in equilibrium. No, we do have some acceleration. Oh, silly me. So we are moving, but that's what we're going to do in a second. But in this direction, we're not moving, are we? We're moving straight up and down the slope. So perpendicular to that, we're not moving at all. As you roll down a hill, you don't just jump off the hill. Do you know what I mean? You go straight down the hill. So this will equal 0. So we can rearrange for r straight away. should be 12 mg on 13. Lovely jubbly. So now we've got that, we can then use that to go down the slope. So if we think about what's putting us down the slope, it's going to be the other component of the weight. So you can think we had cosine last time, so it is sine this way, but same sort of logic. We have that angle, we want this one. The angle's not in there, alpha's not in there, so it's not cosy, it's not cos, it's going to be sine. So mg sine alpha, so 5 mg on 13, putting us down that slope. Putting us back up it is friction. Mu we didn't know, but r we do know now. We have this thing, so it's going to be 12 mg on 13 times by mu. So I'm going to put 12 mu mg on 13. And this now, we are sliding down the slope. So this will be equal to the mass times the acceleration. Mass was just m, and acceleration is just going to be a. What we want to find is that acceleration. So I'm going to rearrange for it. We can cancel out all those m's. We've got one there, one there, one there. And then we've got a lot of bits that are going to be similar. Let me just move this thing out of the way. So everyone's got a 13 on the bottom. Everyone's got a g on the top. So let's take all of those out. So I've got a g, I've got a 13. What am I left with over here? Just a 5. On this side, I've got 12 and mu. So 5, take away 12 mu. So that's good for the acceleration. I'm pretty sure this is going to show that one. So if we look down below, find the normal reaction, we did that. And yeah, 1/13 of g, and then 5 minus 12 mu. So lovely. Yeah, these questions, normally, if you find the acceleration, you've done everything. It might be a case of then just like, oh, we need to actually write down what friction was. So you need to times this by mu, for example. But normally, yeah, find acceleration, or like in the pulleys ones, find tension. If you do that, you've normally done everything else. Last bit here then, part C. What would happen to P if it's released from rest but mu is bigger than 5/12, or bigger than or equal to 5/12? So what we'd have, look over here, if mu was bigger than 5/12, 12 mu would be bigger than or equal to 5. So 5 minus that would be less than or equal to 0. So it's not positive. So our acceleration would also not be positive, because again, all this stuff is positive. So yeah, acceleration would be either 0 or negative. So 0 is not going to move, straightforward. The negative, though, that doesn't mean that we're going to actually accelerate up the slope. Friction is something that just matches us to that point. So what we're going to have is that friction would be stronger than the component of the weight pulling us down. So it would just be exactly equal to that weight, or that component of the weight. Not going to be maximum, not going to be bigger than it, pulling us up the slope, which is going to stop us from moving. So we just sit there. It's basically it's saying there's enough friction to, well, it's down here, enough friction to stop you from going down the slope. You can see there's not a coincidence. This is the same number. This is the way it always is. Like if friction, the coefficient of friction is bigger than or equal to tan of that alpha, of that angle, sorry, then what you're going to see is that there's enough friction, friction's big enough to stop it from sliding down. And the vice versa is true. If mu is smaller than tan alpha, we will slide down the slope. So that all looks good to me. Hopefully nothing too difficult in there. Just resolving forces, solving simultaneously. Let's keep going to number 4. Some variable acceleration stuff. So at time after 1 second, the position is given by this thing. T is 4. The bearing from the origin is 135. Show that C is equal to 3. So first things first, let's plug in the value of 4. Doing that, what are we going to get? So the square root of 4 is 2. So we'll have 2C. And then 4 squared is 16. 16 divided by 8 is 2. So we'll have a minus 6 down there. Bearing of 135. So thinking about that, it's 345 degrees. So we're not north. We're not going to be, what's that, northeast. We're not going to be east. We're going to be southeast. So that is, yeah, 135 southeast. So what we can think about, we must go equal parts right and down. So however we end up with, we must go equal parts right and down. So the down, we know, is 6. So this is also 6, but it is 2C. So let's just draw that out. We're going to have this sort of path, where this must be 6, this is 2C. So therefore, 2C is equal to 6. So this is also equal to 6. So C is going to be 3. You might be wondering about negative, like this being negative 6, but this being positive. It's going down. So that kind of gets the fact, like, you can imagine this is actually the axis here. We're going down to this point, like going down to this southeast corner. So I hope that will make sense. Nice and straightforward. We'll put the right bit in there though. Ooh, where's it going? Right. Yeah, show C is 3. That's always a good sign. Part B then. Find the speed when T is 4. So speed, we get that by differentiating the position. Think speed, meters per second, here meters. So you need to divide this by seconds. Well, not really divide, but differentiate with respect to. So we've got the C is 3 as well. So 3t to the half. Differentiating that, we're going to have 3 over 2. That's not very good numbers. Let's try again. 3 over 2. T to the negative a half. So the half take away 1, gives us negative a half. And here we'll times 3/8 by 2. So we'll get 3/4. Still with the negative out there. And the t, instead of being squared, it's just t by itself. So that looks good for v. We want to do that when t is 4. So let's plug in 4 into there. What does that give us? So square root of 4 is 2. 1 over 2. So flipping it over, 1 over 2. Times by that, it's going to be 3 over 4. And same sort of idea. 4 times by a quarter is 1. So that's negative 3 down the bottom. And they wanted us to find the speed. So we need the magnitude of this. This is velocity, this is a vector. We want the speed, the scalar. So therefore our speed, which you can draw like this. You could draw it without, like, you could just do this as well. It's just like v of 4 without the underline. Make that a bit clearer, that's kind of underlined. But I like the one at the top just to show that it is a vector that we are taking the magnitude of. So what happens when we do that? This is 3/4 and 3. You could do some things like factorize numbers out if you wanted to. Probably worth doing, actually. If we factor out 3 over 4, what do we have? Well, we're going to have 1 and minus 4. So we still want the magnitude of those bits. But the 3/4 coming out, that just stays by itself. So it's 3/4 of 1 squared and 4 squared. So 16 plus 1 is 17. So root 17 on there. So 3/4 of root 17, whatever that pops out to be. Obviously, calculator, you can just do Pythagoras on this, still works. But it can be sometimes quicker to do without the calculator. That's good. That's looking all spot on. Find now, at a certain time in the future, when the acceleration is in the direction of -1 minus 27j. So firstly, let's find the acceleration. We've got our velocity there. We need to differentiate that again. So doing that, we need to negative a half of that. So minus 3/4. Drop in the power, gives us minus 3 on 2. Underneath, we have the power of 1 here. So dropping that down gives us 0. So the t disappears, and we have minus 3/4 out there. Again, I'm going to factorize that. That minus 3/4, let's just stick it out the front. Make our vector a bit nicer to deal with. So minus 3 on 2 and just a 1. Minus 1 2 in the power up there. So we want to be parallel to this. So when we think about that, you can do it in a few ways. Firstly, parallel. We don't need to worry about that really at all, do we? Like the factorization of it doesn't make a difference. We just want this to be something that is going to be equal to like k times a vector of 1 and 27, like that. We can then think about kind of doing the 2 rows, the 2 dimensions we've got, one for the I, one for the j, rearranging both for k, set them equal to each other, and then solving for the value of t. Even easier, think about the gradient here. What that tells us, we're going left 1, down 27. So our gradient is negative 27. So we just want the same thing here, really. We're just going to take the 2 vectors we have, and, well, in this case, the vector we have, and make it have a gradient of 27, or minus 27 in this case. Sorry, no, positive 27. So let's do that. Let's have the y component, or the j component, 1, over the x component, t to the minus 3 on 2, equal to that gradient of 27. You could see how, like, this is I on top of j. You can do it upside down. It's the same thing, makes no difference. Here then, this is on the bottom, but also negative, so I'm just going to, like, cancel that out. So it's just t to the 3 over 2 is 27. And then cube root in that, we get 3. Square in that, we get 9. T gives us 9. And obviously always a good sign if you're getting like something to cube root out and it is a cube number. Very good sign. So yeah, that all looks spot on. Nothing there is concerning me. So we'll continue going on to number 5. We have some projectile stuff. Again, first thing I've spotted, we've got angles. So we know that sine alpha is 3 over 5. Cos alpha is 4 over 5. Leave that over there. What's going on there? We're going to chuck something. What's happening? Small stone, projectile velocity of 35. From a point on the ground, angle is alpha. Initial model, we've got gravity. Hits the ground over here. We've got the path. Its horizontal distance is x, vertical distance is y. So these two together, its position is always just x comma y. It's just always at coordinates x, y. We want to show then that this is going to be true. So relate x and y. So notice here what's missing is the time. Generally, when you're doing suvat, you have time in all of them, don't you? You don't have two different dimensions, one horizontal, one vertical. But we do have two different suvat equations. Well, we can resolve the forces horizontally and then vertically, do suvat in each one, and then combine them via the time. So that's what we're going to do here. So we'll start by doing the horizontal because there's no acceleration. So let's think about what's going to happen. So let's look at our letters for suvat. And this one, yeah, we're going horizontally, where right is going to be positive. So distance traveled is O to A, but they've called that x. The speed, initial speed, is going to be 35 cos. So again, nice and cozy in there. 35 cos alpha, and that's 4/5 of that. So 4/5 of 35. 1/5 would be 7, times by 4 is 28. V, we don't care. We don't know, don't care. Acceleration is 0. That we do care about. That's important. So it's not even suvat. It's just speed distance time. So it is still suvat really, but you can think like, imagine the half AT squared one. The A is 0, so it's just S is equal to UT. So distance is equal to speed times time. So speed is time. T then, do we know T? No, but like I said, T is going to be the link between these two equations. So let's just call it capital T for now. Let's plug in all the bits we do know. So x equals 28t. So I'm going to rearrange 4t. It must be x over 28. This is very useful. This is the bridge then between our horizontal distance and the time we've taken. So if we know one, we know the other. What we can do now then is do suvat vertically, again from O to A. So the height we've traveled, change in height there will be 0. Speed going up initially, well, it was 35 cos this way, so we want sine the other way. So 3/5 gives us 21. V, we don't care about, we do know it's actually going to be minus 21, but we don't really care about that. Minus 21 symmetrical. So what was going up here will be the same speed going down over there. A is going to be negative G, and T will be the same time we found up here. So we have two different dimensions, one horizontal, one vertical. They do not overlap in any of the things that are vectors. So their position, their initial velocity or final velocity, or the acceleration. The only bridge is the time. And in fact, those times will be the same as long as we're thinking about the same journeys in our suvat. Like we're both going from the origin to A in both of them. So yeah, this x over 28 is what goes down here. And then we see, yeah, we don't care about V, so we can start to combine these all together. So S is equal to UT plus a half AT squared. So S is 0, U is 21. T though is x on 28, 28 plus a half of G, so minus G on 2 times by T squared. So x squared on 28 squared. It's not such nice numbers. 21 and 28 is okay. That's 3 over 4 times by the x still minus G on 2 times by 1 over 28 squared. I'm going to assume that's 1 over 160. I will double check on the calculator, but everything else looks right. Like the fact that number's right, most likely this one is 2, but we will obviously just double check. So 9.8 divided by the 2 gives us a 4.9, and then if we divide that by 28 squared is 1 over 160. So that's all lovely jubbly. 6 marks for that. It's very kind of similar, this question, to what you're going to see in other ones. There's not a huge amount of variation. I suppose I've done a little bit of silliness. I've done it to like when it's landing, we could just say that it's not gone to when it's landing, just actually like it's somewhere. So it's not landed yet. Well, it could have done, but we don't know. Doesn't actually change anything. I didn't use the fact that it hit the ground to like affect any of these numbers. Do you know what I mean? This did though. No, because again, this just refers to any part of the journey. Again, didn't use any ending point information. So that's all good. Everything here we've got is completely fine. Yeah, very similar to a lot of the questions though, where you get the two suvats, one horizontal, one vertical. The horizontal is quite simple, doesn't always solve, but gives you a nice relationship that then you can insert into the more complicated vertical version. So yeah, they don't interact with each other apart from via the time. Part B then, what's going to go on? Oh, find the length. Okay, so now we do want to set this equal to 0 and start solving it. So to do that, first thing I'm going to times by 160. I don't really want fractions. So I'll have, like, set equal to 0 then times by 160. So 0 is going to equal 3/4 of 160 is 120. Lots of x minus x squared. So you can see that's much easier to deal with. So it's factorise x and 120 minus x equal to 0. So therefore x is going to be 120 for O to A. Or sorry, O to A is going to be that. X could be 0 or 120. You can think the 0 is the takeoff point, because at that point we were also on the ground. So lovely, that's all good. Using the model, the greatest height of the stone above the ground is found to be h meters. Use the answer, or otherwise find the value of h meters. So two ways of doing this. H meters is the highest point. You can see like here, the kind of the turning point up there. So either we can think about the fact that when we're at that point, it's the transition between us traveling up and us traveling down. So therefore, at that point, we're traveling vertical. We're traveling horizontal. We're not traveling vertical at all. So if we do a suvat that is vertical, our final velocity would be 0. So you would just take this and yeah, to set that equal to 0, solve it however you want to solve it. The other way is to notice the symmetry of this, because our takeoff and our landing are at the same height. Our graph or our trajectory is completely symmetrical. So the midpoint and the highest point are the same point. So yeah, a midpoint and the highest point are the same. They'll be in there. So where our total distance was 120, we can just plug in a value of 60 into there. So that's what I'm going to do. So 3/4 of x, 3/4 of 60 will be equal to 45. This is going to be 60 squared on 160. Let's do that on the side quickly. So 60 squared on 160. 60 is 6 times 10. So that's squared and squared. 16 is 60, well, 160 is 16 times 10. So we can cancel off that and that. 16 underneath, we can write as, that's 2 to the 4. 6 we've got is 2 times 2. Oh, 6, well, 2 times 3, so it's 2 squared times 3 squared times another 10, another 2 and a 5. And you can see then we can get rid of quite a few bits. So we've got 1, 2, 3 2s on the top, 4 on the bottom. So 3 of them can go. What we're left with is 1, 2 on the bottom. And on the top, we've got the 3 squared times the 9, times the 5, sorry. So 9 times 5, 45. 45 on 2. Again, can do that with the calculator, but not such a bad thing to practice every now and then, just to see how you're doing. On good for index laws practice in gymming, not too bad. So we got a whole 45, take away half of 45. What have we got left? Half of 45. So that looks good to me. Yeah, not too bad of a thing. So two ways of doing it. Yeah, like I say, either do the midpoint. That doesn't work if you're takeoff and landing at different heights. The graph is still symmetrical, but the issue is like you'd have, say, this point and this point. So the midpoint isn't the highest point. Like the highest point there is not the actual midpoint of those two. Do you know what I mean? So it's only if you have actually like the same height so that you can see exactly where the midpoint is. Next question on this one then. The models were refined to include air resistance. Using this new model, the greatest height of stone above is found to be k meters. So which one's higher? So if there's air resistance, I think if it's really windy, it's harder to throw things. But another way to think about it is the fact that the air resistance is going to take some energy out of the system. When we released the stone over here, we gave it all the energy it had, all the kinetic energy. So much that is vertical. And in the scenario we started with no air resistance, all of that kinetic energy that was vertical is going to transform into gravitational potential energy and take us up in the air, and then get to the maximum height, and then it will transform back again to kinetic energy, take us back down to A. If we have air resistance, some of that energy is lost along the way from us going from O to our highest position. So because some energy is lost along the way, we must get here with lower energy than we did have, and therefore reach a lower height than we would have done if there was no air resistance. So the new value is lower, whatever they called it. K is the new one, so K is lower than H. Air resistance takes energy out, therefore you don't get quite as high as you would do. One limitation. There's always a few limitations. Spin is just my go-to. Air resistance you can say, but obviously they often ask about that, so it's not a good kind of fallback one to have. But spin, you never get asked about it. At least I've never seen a question asked about it, and you don't learn about how to deal with it. So it's never going to be something that you have not assumed. So it should always be something that is like a limitation, basically. Yeah, so spin should always be the case. The only time it doesn't happen is if you've got like a box on a sled or something on a slope that's not gonna spin or not roll or anything. Do you know what I mean? In that case, it's a particle. We've modeled it as a particle. That's a limitation. So that all sounds good. Let's keep going. Number 6, I think this is the last one. So some moment stuff. So with moments, again, I've seen an angle. First thing to do then, sine alpha, or theta in this case, is 4/5. Cos theta is 3/5. Eagle and money, you might notice that's different to last time. Why is it different? Because our fraction here is different. We have 4/3, not 3/4. Sine is the opposite. Tan is opposite over adjacent. Sine is opposite over hypotenuse. So sine always gets the one on the top. So that's good. Next thing then, let's fill in our diagram with some forces. We have a uniform rod, so it has a mass that's right in the middle of capital M. And there's a little G coming down. It's on a rough ground, so we've got some friction going this way. Does it say what mu is anywhere? I don't think so. And no, we can see later on, find mu. So I will call that mu. And I'm going to have an RA sticking up the ground here, some reaction force. This is mu RA there, acting as friction. And we will have some RC over here as well. I think they call them different things. Yeah, they've called them S. I'm not going to do that. So this is like, what is S is RC. So S is equal to RC. So that's good. How are we going to do that then? So you could go down and just find this value straight away. How are we going to do that? Well, what unknowns do we have? The length we don't have. You can see we don't have the length in there at all. So yeah, we don't have the length, the A. We don't have the RC. We don't have RA. We don't have mu. So 4 things we don't know. If we were to take moments around A, that eliminates the 2 forces that act at A. So RA is gone, mu RA is gone. We're only left with mg and RC. But that would involve moments, so we'd also have the length in each term as well. So we still have 2 variables there, so that's probably not going to be a way to solve it. But it's probably going to be an equation we need. Later on, we want to find the coefficient of friction. So altogether, this is a 9-mark question. And we can solve it without really thinking too much about actually what we're doing, and just starting it in a very similar way, where I want to resolve the forces vertically, I want to resolve the forces horizontally, and I want to take moments around A. The choice of A is kind of arbitrary, but it does eliminate the most number of forces and the most number of variables. So it seems like the simplest equation we can get out. We're going to need 3 in the end. So yeah, we're going to need 3 at the end. So we may as well get the simplest 3 that we can possibly get. So let's see what we've got. Going up, we have RA and some component of RC. What component? Well, again, we can draw that little double axis. Our angle is in here, so it's a bit neater actually. So it's also going to be in the other one, and the other one, and the other one. And we're up here, so do we have this angle? Oh, look, we do. So that's alpha. So we have this angle, we want this direction. Sorry, we have this force, we want this direction. And the angle is nice in between, nice and cozy in there. So we want to have RC times cos. So cos 3/5. So 3/5 of RC. What's pulling us down is the weight of the rod itself. So the big M times by the G, and this is in equilibrium, so that should equal 0. Going horizontally then, putting us to the right, we have mu times RA. Putting us to the left, we have the other component of RC. So we had the 3/5 here, it's going to be the 4/5 for the other one. The 4/5 of RC. And anything else? No. So that's just going to equal to 0. So nice simple equation involving those. Can sometimes be worth like the times by 5. Same up here. Don't know how I'm going to use them yet. So I'm not going to do that just for such a simple step. If it was a case of like combining some bits, maybe. But because it's just times by 5, I'm not going to quite do that just in case there's like another way that might be quite nicer later on. You never know when things are going to be like multiples of 5 later, and everything just cancels out anyway. So next one then, moments around A. So let's think about the clockwise ones. We have our weight, but we don't want the vertical component. We want the component that is perpendicular to the rod. So same sort of idea. Do we need the angle in there? Yes, we do. So alpha's in there. So again, we've got this direction, or this force. We want this direction. Angle's nice and cozy. So we want mg cos. So that's going to be 3/5 of mg. And then in the other direction, oh, and times by a, sorry. So 2a for the entire length times by a then for how far away that is. If this whole length is 2a, how far away this is being the middle of that must be 1a. So we times this by a. Similar sort of thing then for the RC going the other way around. We're going to have 1.5a, so 3/2. The value of RC. And the, again, do we need any component? No. This is already perpendicular sticking out here. So we don't need any cos or sine or anything there. This will just equal 0. But we do need, again, a. 3/2a should be in there. This will equal 0. And this will actually cancel out our a's. You can do straight away. A there's gone, a there's gone. 3 there's gone, 3 there's gone as well. Let's see the cancel in there. So what we're left with, we think if we just double everything, that gives us RC. So therefore RC is going to be equal to 2/5 of mg. Nice. So you might think, why did I actually do these equations first? Well, because we could have just done here and gone straight to this one. I had a little bit of a brain fog earlier. I didn't realize that the a's are going to cancel out. They're going to be everywhere and just cancel out. So we could have done that equation straight away and got this one. Why haven't we? It's because now we're able to walk through and solve a lot of things very easily. Because if we look above, here we know what RC is. Let's plug that in this equation and find what RA is going to be. Well, we've got 3/5 of RC, so 3/5 of 2/5. That's going to give us 6/25 of mg. Let me just move that over a little bit. Minus mg equals 0, and still plus the RA at the front. So copying from this equation, plugging RC in. So 6/25. This would be 25/25. So 19/25 is like the difference. So RA is 19/25. You can think this is 25/25. Add that over, and then take this one away. So RA is going to be, what did I say? 19/25 mg. And now we're able to look at this one and get mu out. So if we rearrange that for mu very quickly, I'll do it on this right hand side over here. Mu should be equal to 4/5 lots of RC over RA. So let's plug those bits in. RC, 2/5 of mg. But we want to have 4/5 of that. So 8/25 altogether times by mg. Bottom, we just worked out 19/25 lots of mg. Now lots of bits are going to cancel. Goodbye m, goodbye g, goodbye m, goodbye g, goodbye 25th, goodbye 25th. What we're left with is just an 8/19. The fact that everything cancelled off there again, good sign everything's correct. Was that the last question? I think it was. Let's double check. Yep, that is. So like I say, yeah, I think that all looks good. I will go through and double check, make sure everything's correct. If this is the end of the video, that was all correct, then it's a good sign. Mechanics, it's very straightforward. It's very similar every time. You get some equations out, and then you solve them like simultaneous equations. That's basically it, unless it's the variable acceleration stuff. So even think if we look back at this suvat one, we get one equation, we get another equation, we get we combine them together to get a third equation out. And then what do? We just solve some stuff with it. In this one before, variable acceleration, bit different, differentiation, integration, but not still too difficult for an idea to do. You can differentiate, should be hopefully be doable. Here, same sort of idea. You've just got equations out, and you're just going to solve them. In this case, not even simultaneously. We just solve them individually, and everything pops out. What's going on here? Speed time graph. This is kind of just still suvat. So getting equations out, solving them, and still getting different types of simultaneous equations out, just solving them straight away. So mechanics, very repetitive. Try and just think about what type of question is it. Do I need to draw forces? Is it variable acceleration, or is it suvat? It's pretty much always one of those three, or the kind of very rare. These are very rare, actually. You don't see too many of these. They're pretty much always one of those three types. And then if you can just learn them in like the three methods I do to approach these, it should make them all a bit more straightforward. So any questions, let me know below. If there's a specific past paper you want to do, give me a shout. If not, I'll just keep kind of doing random ones. But yeah, thanks for watching. I will see you next time.